this is h of y minus h of y given x. If I know x, then h of y given x is h of p. And this is less than or equal to 1. And so we have this. This is less than or equal to 1. And it's achieved by p of x equals a half-half by a uniform distribution on the input gives you a uniform on the output, and you achieve it. All right, great. But are these distinguishable? I've calculated this mathematical formula. Over here, it was easy to identify how you would get a distinguishable subset. Here, it's not at all clear. So let's take a 2-minute break, and when we come back, I'll show how this, if you repeat it, is nothing more than this. All right, 2-minute break. I have the solutions for those who have handed in the homework. Just pick up a copy of the solutions to the homework there.
There's no homework this week?
Yeah, no, I'll hand out the homework next Tuesday. Okay, here's the trick we're going to use. Trick. Repeat channel n times. So this is the nth extension. Now, the alphabet is of size x to the n. And the output alphabet is of size y to the n. Now, look at this. For every xn here that we send, if xn is typical, what do I mean by that? P of xn is essentially 2 to the minus n h of the distribution. So I'm going to fix P of x. And so this probability is 2 to the minus n h, roughly. So how many typical ones are there? 2 to the n h of x. So once I've fixed the input distribution P of x, I now have 2 to the n h of x typical input sequences. Typical means their probability is what they should be, 2 to the minus nh plus or minus epsilon. Have I left any out? Yes, I have. Is the total probability of them small? Yes, it's as small as you wish. Now, the size of each of these is 2 to the n h of y given x. And we'll prove that to our satisfaction. Right now, this is a heuristic argument. So, this is a noisy typewriter. How big is this output alphabet? 2 to the n h of y. That's the number of typical output sequencers. If you put the x's in, IID, according to P of x. So now we just fix our attention on the typical sequencers, input, the typical output sequencers, and if you wish, the conditionally typical y's given the x's. We'll use the term joint typicality for an xy pair that is typical in x, typical in y, and typical jointly. Now, I ask you, how many distinguishable inputs are there? Well, I don't know. It's a mess, just as this is a mess. If I tried to use them all, I'd be confused. But if I choose a subset of them, then I'm not confused. So how many, if each fan has this number of elements, maybe the number of distinguishable fans is 2 to the n h of y, the total number of possible outcomes, divided by 2 to the n h of y given x, the amount in each fan. But that's 2 to the n I of xy. So this would help to prove a converse that says I can't get more than I of xy bits through a channel that looks like that. In other words, the number of distinguishable ones here can't be more than the number of non-overlapping fans. You could say it's a little daunting. What do I mean by non-overlapping? I mean the probability of the intersection and so on. The original page, look, Shannon did an outline, and in 1956, Feinstein wrote a 56-page paper proving this and some other things, which was considered the first rigorous proof, but really it was just the first detailed proof. Because Shannon outline can be fulfilled, and that's what we'll be doing later. So it was just an outline. Even a rigorous proof is an outline of a proof. It's just the gaps are smaller. All right. So this would give you the converse. And now to prove that you can get a distinguishable subset of these, choose these at random. Choose 2 to the nr at random. As long as r is less than I of xy. We have a chance now that these don't intersect. And indeed, a random packing of these output fans is as good as you can get to first order in the exponent. In other words, you can achieve channel capacity by choosing a random subset of these x's, as long as the number of elements, input sequences you choose has an exponent less than the mutual information. All right. So now you see what we've done. By repeating the channel many times, we've shown that every channel that's memoryless can be considered essentially like the noisy typewriter channel. And then all we have to do is show that a random choice of the inputs, as long as you don't choose too many of them, can be distinguished. So that's the key. It's quite amazing. Let's take pennies. Well, let's take intervals. How many intervals of length 1/100th can you fit in the unit interval? Oh, chunk, 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 chunk. 100 of them. How many pennies can you fit on the plane? Well, hexagonal closest packing. So you calculate it. That's the number of, just say if the penny is the size of the noise, the center of the penny is what you send. Right? Now, if you throw down pennies at random, you don't get a very efficient packing. Well, this is packing pennies, or whatever you might want to call this, in n dimensions. Do you get an efficient packing when you go to n dimensions? I've already shown that going from 1 dimension to 2, you lose the little hexagonal bump outs. And the answer is yes, amazingly. It's wonderful. By the way, if you can show that a random subset will incur a small probability of error in the decoding, you're done. Because there's at least one code, one choice of these that's as good in the probability of error as the average. And I've said the average has small probability of error, average over all codes. So it's really the random coding argument, which is used here for the first time in the Shannon argument, it yields an existence proof, because there are only a finite number of finite alphabet codes. And so if there's one that has small probability of error, if the average has small probability of error, then one of those finite number will have small probability of error. So we've used random coding not because we're going to send something random when I want to send something deterministic, but because I've used random coding to show that there exists a set of distinguishable inputs as viewed by the outputs. And they're 2 to the n number. All right. So, time to calculate some more channel capacities. Examples of C. 1, a binary symmetric channel with crossover probability P. C is 1 minus h of P bits per use. What does that look like? Here's 0, 1, and here's P.